Assalamu alaikum, everybody. This is our last lecture for the course, inshallah, and it is titled Memory Management. Now, memory management is not really a data structure per se, but rather it's going to show us an application of data structure, a real application of data structure. In this case, to do memory management, which is one of the functions of the operating system. So here are the topics. We explain what memory management is all about, and then discuss the two main ways of doing memory management. We have sequential fit methods, and then there is non-sequential fit methods. We shall explore one particular example of non-sequential fit memory management method, and these are called buddy systems. Okay, the last topic will be about garbage collection. Okay, so hopefully it's going to be a very short lecture. These are the only topics that we're going to study. Memory management. First, we note that the heap is the region of main memory from which portions of memory are dynamically allocated to programs upon request. Of course, heap here should not be confused with binary heap that we discussed in one of our lectures. No, heap is an area of the RAM from which memory is allocated to programs by the operating system. So when you start your program like Microsoft Word or NetBeans or any other program, the program will make a request to the operating system that it needs a certain amount of memory, and the operating system will allocate that memory. Now, the operating system actually has a special component called memory manager. Okay, so here it says a component of the operating system called the memory manager is actually the one responsible for memory management. And among the things it does include the maintenance of free memory blocks. It needs to know within the heap which blocks are free and which ones are not. And it does that actually by making use of a data structure like linked list, as we shall see. Okay. It also assigns specific memory blocks to the user programs. So when a user program makes a request for memory, it is the memory manager that will allocate the requested memory. Since it knows which ones are free and which ones are not, it is the one that will look among the free blocks which one can satisfy the request, and it will allocate such block to the program. Okay, it does the opposite as well, cleaning memory from unneeded blocks to return them back to the memory pool. That is after a program finishes or terminates, then the memory allocated to it will be reclaimed by the memory manager and put back in the pool of free memory. Okay, and the last thing it does is defragmenting memory blocks when needed. Now, defragmentation means, well, before we explain the defragmentation, let's explain fragmentation. Fragmentation means having small pieces of memory in many places within the RAM, but they are too small to be allocated to a program. Okay, 1 byte here, 2 bytes there, 3 bytes here, and so on. If you add them up, they will form a tangible amount, but because they are not contiguous, they are not one block, they cannot actually be used. So they are considered to be fragmented. Now, one of the functions of the memory manager is to defragment the fragments, meaning to join them together into a bigger block so that they can be used to allocate to other programs. So these are the main functions of the memory manager. But before we proceed, let me just explain about this fragmentation, because it can be of two types. Okay, so it says there are two types of memory fragmentations that the memory manager has to deal with. One is called external fragmentation. Okay, external fragmentation is the presence of wasted memory outside the allocated segments. So within the free memory blocks, there are small chunks here and there that cannot be utilized. Okay, this is called external fragmentation. Fragmentation within the free blocks, outside the ones that are allocated to programs. The other type of fragmentation, which is called internal fragmentation, is the presence of unused memory inside the allocated segments. So the memory manager has allocated memory to programs, but the program doesn't use some of those memory blocks because they are too small, or because it doesn't really need them, as we shall see. So basically, if the fragmentation is within the allocated part, it is called internal fragmentation. If it is within the unallocated part, within the free memory blocks, then it is called external fragmentation. We shall explore these two types of fragmentation as we look at the two main methods of memory management. Okay, let's start with the sequential fit methods. In sequential fit method of memory management, all available memory blocks are maintained using a single linked list. So one linked list is used. Inside the linked list, we will have information about the addresses of memory blocks that are free. Okay, along of course with their sizes. Right. So if a program makes a request for memory, the memory manager will search the list to find a free block whose size is larger than or the same as the requested size. And then it will remove that block if it is equal to the size. If it is not equal, it will break it actually and take part of it and assign to the program that made the request. Okay, so this is how it will do it. The question now is, how does it search the list? Right, now there are many different strategies for searching the list to satisfy a given request. So there are different searching strategies. So searching is done using one of the following strategies. Okay, and the first one is called first fit. So the memory manager will allocate the first block of memory large enough to meet the request. In other words, it will start the searching from the beginning of the list until it finds the first block whose size is big enough to satisfy the request. So it will allocate from that block. If it is equal to the requested size, it will just allocate it. Otherwise, it will break it and take the part that is needed and keep the balance. So this is called first fit. First fit because searching from the beginning, the first one that it finds is the one that it will allocate. We will see example in the next slide. Okay. Another strategy is called best fit. So here the searching could take a little longer actually, because the objective here is to try to avoid fragmentation, okay, external fragmentation in this case. So the idea is instead of just finding the first block that will meet the request as done by the first fit, no, it will search the entire list and find the block that is closest in size to the request. So the program requests for 8 bytes. It will search the list and see which block is 8 of size 8. If not 8, then the next number higher than 8, and so on. Okay, so the idea is so that we don't break. For example, this one, suppose we have 10, a block of size 10, and a request is made of size 8. Then the first fit will break the 10 into 8 and 2. Okay, allocate the 8 and keep the 2 bytes. The problem is these 2 bytes may never be used because probably no program will request just 2 bytes. So the 2 bytes will become fragmented. Whereas this method will try to see if it can find exactly 8 first. Only if it cannot find, then it will look for the nearest size and then break it as the first fit will do. Allocate what is needed and keep the balance. The next strategy is called worst fit. This is ionic, isn't it? Why should we have a worst fit? Okay, well, worst fit, what it does is it finds the largest block on the list and allocate from it. Okay, the idea again is to avoid fragmentation, because if it finds the largest block, chances are that if it allocates from it, what is left will still be large enough to satisfy the next request. So there will not be fragmentation. Okay, so that's what is being explained here. It finds the largest block on the list so that the remaining part is large enough to be used in later requests. Okay, so this is another method. And the last strategy is next fit. Now next fit is the same as the first fit. Okay, same as the first fit, but the search starts from the present position instead of starting at the beginning of the list. This is the idea. So as the memory manager searches the list, for example, if it finds and allocates a block somewhere in the middle, it will have a pointer that will remain at that middle, doesn't come back again. So that if there is another request, it just continues from its current location, from the middle, forward until it finds the requested size. If it doesn't find them, of course, it will cycle back so that it will search the whole list. So the whole idea is it is trying to optimize the search so that it doesn't always search from the beginning. It will start from the current position. Now we're going to see the example of these strategies in the next slide. Example, so in the following, figure A shows list of free blocks where the numbers indicate the addresses of the first byte. Okay, so this is the figure. It's directly from the book, figure 12.1. Here the light gray blocks are the ones that are free, whereas the dark gray are allocated, they are not available. Okay, now the numbers here indicate the address of the first byte. Actually, this is how you address a memory block, just by telling what is the address of the first byte. Okay, so for example, you can see if this is size, its size, the small one here its size begin at 10, it means this free block is actually of size 10. Okay, this on the other hand, it starts from 12 and the next one start at 21. Therefore the size is 9. Okay, if you subtract 21 minus 12, you will get 9. Okay, and so on and so forth. This is another block which seems to be big enough, between 60 and 70, is also of size 10. And this is the largest block. From 70, we don't know exactly to where, but at least by looking we can see that it is clearly larger than any other free blocks that we can see. Okay, so suppose a memory manager is maintaining these free blocks. Basically it will have a linked list that will say, okay, I have a memory of size 10 that starts from address 1. I have a memory of size 9 in another node, if you like, of the list. There is a free memory block of size 9 starting from address 12, and so on and so forth. This will be the content of the list, information about the free blocks. Okay, now let us see how each of the 4 strategies that we mentioned in the last slide will work if a request is made based on this configuration. Okay, the figure B shows what the different strategies will do in order to allocate 8 bytes of memory. So there is a request of 8 bytes from a certain program, and we want to see how the different strategies will allocate the 8 byte requested based on the information we have here. Figure B here shows what will actually happen. Alright, the request is for 8 bytes. So the first fit will start the search from the beginning of the list. The first block that it finds that is either 8 or greater than 8 will be used. So here we have a size 10 free block as the first block. So first fit definitely will allocate from this block. What it will do is it will break the 10 into 8 and a balance of 2. Okay, now here this is an example of external fragmentation. We have a balance of 2 bytes here, which is too small really to be used by programs. So if we have many such small blocks, we know that they are basically wasting the memory, and therefore they are called fragmentation. And because they are within the free blocks, this is called external fragmentation. Okay, so this 2 bytes that will be left out of this 10 is going to be externally fragmented. Okay, what about best fit? What will it do? Now the best fit, as we said, it will search the whole list and find the block that is nearest in size to the request. Okay, this is size 10, this is size 9. This we don't know exactly, but clearly is less than 8, and these are all smaller. This is 10, this is more than 10, and therefore the best one that is closest in size to 8 is this one of size 9. So this is actually the one that the best fit method will choose, or the best fit strategy will choose. But like the best first fit method, it will break the 9 into an 8 and a 1 byte. Okay, so the balance of 1 byte here again is externally fragmented. Okay, good. What about the worst fit? The worst fit, as we said, it will search the list and find the largest block. The largest block seems to be this one, the last one here. So worst fit will actually allocate from there. So the idea is what is left here is big enough so that next time probably it can be used to service another request. So in this way, this is not fragmented because what is left is big enough to satisfy another request. So it tries to avoid fragmentation this way. Okay, so although the name is worst fit, it looks like it is actually very good. It's trying to avoid fragmentation as much as possible. Now, the last strategy is called next fit. So here we're going to make some assumption. Assuming the memory manager is currently at this point, okay, at the point that the request of 8 bytes is made, its pointer was here. Maybe it serviced some request earlier on and it was positioned here. So now if a request of 8 bytes come in, it doesn't start searching from the beginning. No, it searches forward. And as you can see, the next block it will find that is greater or equal to 8 is this one, size 10 again. So it will allocate the 8 bytes from that block of size 10, and again there will be a balance of 2 bytes which may be externally fragmented. So this is basically how sequential fit methods they work. They are called sequential in the sense that they are searching the list sequentially, okay, linearly, until they find the correct block that can be used. All right, and this is what we want to say about this strategy or this method. Next method is non-sequential fit methods. Okay, in particular we want to look at what are called buddy systems. Okay, a buddy means a friend. So in this method, instead of having a single linked list of free blocks, an array of linked lists is used. So many linked lists, an array of them, many of them. Each list holding blocks of the same size. In particular, one type of buddy system is called binary buddy system. Okay, now in binary buddy system, the heap is viewed as one large block which can be split into 2 equal smaller blocks. So that is where the binary comes from. The blocks are being divided into 2 and then into 2 again and then into 2 again. So the division is always into 2. And when you divide a block into 2, the 2 parts are called buddies. Okay. So for example, for a memory of size M, assuming the heap is of size M initially, then the free list will consist of linked list of the following or containing memory of the sizes. So we're going to have a linked list containing 1 byte only. 2 to the power 0 is 1. We have another linked list that will contain 2 bytes and then 4 bytes, 8 bytes, 16 bytes, and so on. 2 to the power k. Okay, so we can only keep track of memory in powers of 2. This is why the buddy system in this particular one is called binary buddy system. Okay, so we will have all powers of 2 as long as 2 to the power k is less than or equal to m. Let us see that diagrammatically. Say each array element, okay, so this is our array, will contain a list of free blocks. Okay, so it will contain a linked list but the linked list will contain 3 blocks of the same size. Okay, so here this configuration, so far there are no 1 bytes, no 2 bytes, but we have many blocks of size 4 bytes. 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, no 3 blocks of size 8, but there are 3 blocks of size 16. 1, 2, 3, 4, 5, 6 of them. Okay, and we have a linked list of size 32 bytes, a linked list of size 64 bytes, a linked list of size 128 bytes. So this is the idea. Instead of having one linked list, having memory blocks of different kind of sizes as in sequential list method. No, the binary body systems will have several linked lists in an array. So array of linked lists, similar to, if you recall, what we have with graph, where we represent the edges as array of a linked list. So this is an array of linked list, but each cell in the array will contain a linked list of memories of particular size, where that size must be a power of 2. Okay, we're going to take an example actually to show how the memory manager will allocate memory using this system. Okay, so here it says each memory block has its body, and given the address of a block, the address of its body is very easy to compute. This is actually one of the most important aspects of this body system. Computing the address of your body, if you know the address of its body and the size, is very easy. Okay, this is the formula. Say the body of a block of size 2 to the power k that starts at address x is the block of the same size 2 to the power k that starts at address y. How do we get y? Simply by complementing bit k in the address of x. So our block A, for example, of size 2 to the power k has address x. The question is, what is the address of its body? Let's say block B. Of course, B will have the same size as A, so it is also of size 2 to the power k. The question is, what is the address? Where is it? Where is it in the heap? Well, to get the address of the body B, all you need to do is take the address of A and complement bit number k. Okay, where bits are counted from right to left, starting from 0. Okay, so in the bits representing the address here x, you start counting from right down to left, and you're going to start counting from 0 until you reach k. So the k's bit is the one you should complement to get the address of the body. Let's see an example. Consider this small memory segment of size 8. Okay, 8 bytes, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so suppose they are addressed like this. This byte is 000, 001, and so on. Obviously, with 8 cells, if you are using bits, you need a word of length 3 to allocate them addresses uniquely. Okay, now what we want to see is how this formula works. Okay, suppose you are considering an address, a block of 1 byte. Okay, so only this 1 byte, and its address is 000. The question is, what is the address of the body of this block? Okay, so all you have to do to know the address of the body is take the size. Well, the size is 1, so convert 1 as a power of 2. Obviously 1 is equal to 2 to the power 0, which means k is 0. Therefore, to get the address of the body, just complement bit number 0. We're going to be counting the bits 0, 1, 2 from right to left. So this is number 0. Just complement it, it will turn to 1. Of course, complementing means change it. If it is 0, change it to 1. If it is 1, change it to 0. So if you complement 1, you're going to get 0, 0, 1. So essentially telling you this is actually the body of this guy. Okay, this is what this black arrow means, that these two are bodies, memory blocks of size 1. Okay, if it is this one that you know and you are looking for the address of its body, the same thing, just complement bit number 0. You will get this. Okay, what about this? Okay, so again, this is the address. To get the body, since the size is 1, just complement bit number 0. And this is what you have. And similarly here, if you complement this, you get this back. Okay, you can see the same thing is happening here. This and this are complements. Therefore, considering them as addresses of size 1, they are bodies. And similarly for the last one. Okay, so this is how to know the address of a body. Now let's look at the case where the addresses are not of size 1 but of size 2. So you consider this as one block, the first 2 bytes. Okay, now as we said earlier, the address of a memory block is actually simply the address of the first byte in that block. So even though it is 2 bytes, this is still its address. Okay, this 2 bytes, this is its address, and so on. The address of a memory block is simply the address of the first byte in that block. So now, considering these 2 bytes as a block, given that the address is 0, 0, 0, how can we find the address of its body? Well, the same formula. The size is 2 this time, so convert 2 to be a power of 2. So obviously 2 to the power 1 is equal to 2. So which means k is equal to 1. Therefore, to get the address of the body, you need to complement bit number 1. So counting from 0, 0, 1. So this is the bit, the middle one that we need to complement. So you're going to get 0, 1, 0. Now if you look, this is 0, 1, 0. So essentially what you are saying is the body is this guy. Another 2 bytes with this address is the body of these 2 bytes. Okay, so this is what is being shown in red arrow here. Okay, so these 2 blocks of 2 bytes, they are bodies. Similarly, these 2 blocks of 2 bytes each are also bodies. See, if you complement this middle element, you have 1, 1, 0. Well, that's exactly the beginning address of the other 2 bytes. So these 2 are bodies. Okay, and the last one here is showing you the same thing, but taking the size to be of size 4. So if you take these 4 bytes as a block, the address is still 0, 0, 0. What will be the address of the body? Well, 4 is the same as 2 to the power 2. So k is equal to 2. Therefore, just complement bit number 2, counting from 1, from right to left. So 0, counting from 0, sorry. So 0, 1, 2. So this is the one we need to complement. In other words, we're going to get 1, 0, 0. Okay, 1, 0, 0 is here. You can see from here to the end is another 4 bytes. Okay, so this is the body of this first 4 bytes. If you complement this, you're gonna get this. So the body of this is this, like that. So this is the idea of body system. It allows you a very easy way to split memory block into 2 by computing the address like this. Okay, I'm going to take another example, this time with a bigger block, just to make sure you understand this idea. So suppose a memory block A has a size of 256 bytes and its address is given as this. What is the address of its body? Okay, this is a very common question in exam, so you need to be able to know how to compute the address of a body if you are given the size and address of its own body. Okay, so as we did in the previous slide, all we have to do is convert this size to a power of 2. Okay, so it's a first we express the size as a power of 2 to find what is k. Well, 256 is actually 2 to the power 8. So it means k is equal to 8. Therefore, all we have to do is complement bit number 8, counting from 0 and starting from the right to left, in the address of block A. That will give us the address of the body. So counting from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. So this one is the only bit that we need to complement to get the address of the body. Okay, therefore the address of the body is this. Okay, so this is how to find the address of a block given the address of its body and the size. All right, and with this we can now introduce the idea of how body systems actually allocate and deallocate memory, or acquire and release memory. So the following are the algorithms for allocating, which is also called acquire, and releasing memory, which is called release, in body systems. Okay, acquire. To allocate a memory of size x, where x is less than or equal to 2 to the power k, the body system will search the corresponding free list. Remember, we have many free lists, each one representing a certain size, which is a power of 2. So we're going to search within the linked list of size 2 to the power k. If there is a free block there, then it is a simple matter of taking one of them off and allocate it. Okay, if there is a free block, if there is a memory block in the linked list of 2 to the power k, we just allocate. But that list may be empty. There are no memory blocks of size 2 to the power k. So what do? We look up in the linked list of 2 to the power k plus 1. Is there are there free blocks there? If there are, then we're going to take one of them, okay, divide it into 2 bodies. One body is put in the free list of the lower size, which means it will be put now in 2 to the power k. There will be 1 in 2 to the power k, and the other body will be allocated. Okay, what if 2 to the power k is also empty? We go up again to 2 to the power k plus 2. Take one block there, break it into 2, put 1 in the linked list of 2 to the power k plus 1. The other one again further divided into 2 Okay, put the one half or one body in the linked list of 2 to the power k, and then you allocate the other one, and so on and so forth. If this is not available, you again go to the next higher linked list, and so on until you find one, and then you make the allocation. We shall see a practical example of this after this slide. What about release? So a program has finished its use of the allocated memory, and the memory manager needs to return it back to the free list. So this is the procedure: release X. So the block is placed back in the free list of its size. Okay, but we don't stop there. We check if its body is also free. The one that has been returned, its body is already available. So we don't keep two small pieces together. Rather, we combine them together to form a free bigger block of size 2 to the power k plus 1. And we try to put it in the linked list of size 2 to the power k plus 1. But again, if that one also has a free body in the linked list of 2 to the power k plus 1, they are again merged together to form a bigger block of 2 to the power k plus 2. And then you attempt to put that back into the linked list of 2 to the power k plus 2. And the process is repeated until either we form a block that is the entire size of the heap, or until we meet a situation where the body is not yet available. Okay, the body is not yet available, so just put this one until that one returns, then the combination can be done. Okay, yeah. So this is the idea. If its body is free, they are combined to form a free block of size 2 to the power k plus 2, which is then moved to the appropriate free list, and so on. The process continues. Now, to put this into practice, let's take an example. Suppose you have a system consisting of a total of 1 megabyte. Okay, so this is the old good days where memory is very scarce. So assuming you have a computer that is totally only 1 megabyte available. Now suppose a request is made by a program requesting for 10 kilobyte, 100 kilobytes. Okay, by the way, the situation here means at the moment, among the array of linked lists, only the one of 1 megabyte has a block, and that block is also one cell only, okay, of size 1 megabyte. The linked list of 512 or 256, 64, and so on until linked list of 1 byte, they are all empty. Only the linked list of 1 byte is not empty, it has one block of 1 megabyte. Okay, so suppose a request is made of 100 kilobytes. How will the memory manager allocate the 100 kilobyte? Well, the first thing it does, of course, it will search the linked list of the next power of 2 bigger than 100, which is 128. Okay, this is actually one of the disadvantages of body system. It has internal fragmentation, because you see here, although only 100 KB is requested, the system cannot allocate 100 KB. It has to allocate a power of 2. So in fact 128 is going to be allocated. And since the program is only going to need 100, the remaining 28 bytes are internally fragmented. Okay, internal fragmentation within the allocated memory. All right. Okay, but let's come back to our problem. We want to allocate 100 kilobyte, So no memory in 1 kilo in the linked list of 128. We check. How about 256? Nothing. How about 512? Nothing. How about 1 megabyte? Yes, there's a block. So break it into two. Remove it, of course, from the 1 megabyte linked list, and then break it into two. Half of it, which is 512 kilobyte, put them in the linked list of 512. The remaining 512, break it. Actually, let me show you the output here. The remaining 512, break it further into two, 256 and 256. Put this 256 in the linked list of 256. So now the linked list of 512 has one block. The linked list of 256 has one other block. But the remaining 256, we again have to break it into two. Okay, we will have 128, 128. The one of the 128, put it in the linked list of 128. So we have three blocks, three free blocks in three different linked lists of size 512, 256, and 128. It is the other 128 kilobyte that we are going to allocate to the program. Okay, so we are calling that allocated block A, and we are shading it in yellow color here to indicate that it has been allocated. So this has been allocated. Okay, if you are drawing the linked lists, obviously all others will be empty, except the three linked lists of size 128 will have one block, 256 will have one block, and 512 will have another block. All right. Now suppose there's another request of size 240 kilobyte. Okay, so we search. This is the first list we're going to search. We have to search for the list with size greater or equal to this. Immediately greater, not the biggest size. So 240, we cannot allocate 128, it's too small. We have to allocate 256. So we're going to allocate, we find this time there is a block, so we allocate it directly. And therefore, this is the configuration after that. So now the linked list of 256 is also empty. We only have two free blocks, one in the linked list of 512 and another in the linked list of 128. Okay, we have another request of 64 kilobytes. All right, so no element is found in the linked list of 64. So we go to the next upper block. We go to the next linked list, which is of size 128, and we find there is a free block. So what we do, we break it into two. We're going to remove it from the linked list of 128, break it into two bodies. One body will be put in the free block of 64, and the other one will be allocated, as you can see here. So this has been allocated. We're going to call it C. This is B. This is A. So just so far, these are the blocks we have allocated. All right. And now we have two free blocks, one in the linked list of 64 and one in the linked list of 512. Another request come in, requesting for 256 kilobytes. Well, the linked list of 256 is empty. So we have to go to the linked list of 512, remove the only one block there, break it into two, put one in the linked list of 256, and allocate the other. So this is what happens. This has been allocated now, and this is now available in the linked list of 256. All right. Now, suppose block B is released. Okay, this is block B. It is released. The program that requested for it has exited, so it can be returned back to the free memory blocks. So how will the release work? Well, release will return this block in the linked list of 256. However, it will try to check, is the body of that block available? This is the body of that, and clearly it's not available. Part of it has been allocated. So this will be placed in the linked list of 256 for the moment. It will remain there. All right. Now, suppose A is released. So this was A. The program that requested for it has terminated and the memory is being returned. So it will be returned. An attempt will be made to see if its body is available. Unfortunately, its body is also not available. So it will simply be placed in the linked list of 128. Okay. Now, this is one of the, again, if you like, disadvantage of body system, because apart from having internal fragmentation, as I explained earlier, it can also have external fragmentation. Because you see, we have 256 here, but we cannot combine it with 128 to form a bigger block until the body of this guy is returned. Only then we can combine and now put them in the linked list of 512 and so on. So suppose now your request or your request comes in with 75 kilobytes. It's a big problem. This actually is showing internal fragmentation, because 75 definitely is bigger than 64, so we cannot use the linked list, the free block here of 64. We have to allocate as big as the next size, which is 128. Okay, so there is a 128 available, so we're going to allocate it. But look the difference. The request was only for 75, but just because 75 is slightly more than 64, we have to allocate almost double the size, which is 128. So a huge internal fragmentation here. Okay, because that program will never need more than 75. This is why it made this request, but we are allocating it 128. Okay, so we allocate 128, we call it E, and again in this block, this is the only available one, so we cannot merge to form bigger blocks. Now suppose C is released. So C is released. It means we can combine now. We will not just put the 264 together as separate blocks in the linked list of 64, because this is the body of this one. They will be merged together to form a block of 128. So now we're going to have two blocks of 128, and therefore, we're going to have a block of 128, so it's going to be put in the linked list of 128. So the linked list of 64 is now empty. This is the point. Okay. Once a body return back, they are merged together to form a bigger block, and the block will be put in the linked list of the bigger size. All right. Now, suppose E is returned. Now, this is good news, because E returning means the body of this guy is back, so they can be combined to form a bigger block. Not only that, it means the body of this guy is now back, so they can all be combined to form a bigger block of 512. Of 512. Okay. But this block of 512 cannot be combined with this one, because this one is not yet fully available. So this is what you have after releasing E. Okay, you will have this all combined to form 512. So now we have two free blocks, one in the linked list of 512, one in the linked list of 256. Suppose finally we have D released. So if D is released, now it's a good news, because its body is already free. So it will not just be returned in the linked list of 256. No, the two bodies will be combined together to form 512. But that 512, its body is also available. So the two will now be combined together to actually form a megabyte, just like we started earlier. So this is essentially how the body system works. As you can see, as I will summarize here, among its advantage is fast allocation of memory. All what is needed is a simple recursive splitting operation, because once we know the address of a body, we can easily compute the address of the other body, and so on. And similarly, there is a fast memory release. Okay, much faster actually than sequential methods. So this is the advantage of body system: fast memory allocation, fast memory release, fast combining of free memory, because of the simple way that you can get the address of a body from its own body. But there are disadvantages, as we already observed. There is a huge internal fragmentation, especially if the requested size is slightly larger than a power of 2. Just slightly larger, then we have to take the next power of 2, which may be almost double what is requested. Okay, there is also external fragmentation, because we can only combine a free block if its body is also free. So it will remain small until the body comes back, then we can combine them to form bigger blocks. So in that sense, there is also external fragmentation. There are small blocks within the unallocated part that cannot be combined to form larger blocks until the body is back. So this is basically about the body system. The final topic we discuss is garbage collection. All right. So first, what is a garbage? A garbage is any memory that was allocated to a program and is no longer being referenced by that program. Okay, to give you an example, suppose you create a student object. So you said student Ali equal to new student. You give the ID, you give the name, and you give the GPA, for example. So obviously an object will be created, and the variable Ali will reference that object. Okay. Suppose you create another student Khalid, similarly with ID, name, and GPA. What will happen? Another object will be created, and the variable Khalid will reference it. Now, what will happen if you say Ali becomes Khalid? So you do an assignment that says Ali becomes Khalid. Basically, what you are saying is assign the address of Khalid to be also what Ali will point to. So assign the address of Khalid to Ali, meaning Ali will also point to the same object as Khalid. The issue here is this object of Ali now has no reference pointing to it. It was being pointed by Ali, but now Ali is pointing to this object just by making this assignment. Okay, now this is what we call a garbage. A garbage is memory that was allocated but is no longer being referenced by the program. Okay, now garbage collection is the process of locating this type of memory that are no longer being used and returning them back to the pool. Okay, so this is just explaining that now Ali object becomes garbage. It is on reference object. No reference is pointing to that object. so it is called unreferenced, and therefore it's garbage. Now in Java and other object-oriented languages, the garbage collector is automatically invoked to collect unused memory cells when the program is idle or when memory resources are exhausted. Okay, so this process is not continuous actually. The program will do it occasionally. For example, when the program is idle, no activity is going on, so the garbage collector can quickly be run and return all garbage, reclaim the memory, and then the program can continue. Of course, if the memory is being exhausted, then at that point it becomes critical to run the garbage collector and clean the garbage and return all the memory back to the pool. Okay. Now we're going to look at there are many ways of garbage collection, and we're going to look at two of them. Okay, so it says here two popular garbage collection methods are mark and sweep and stop and copy. Okay, let's look at mark and sweep. Mark and sweep is a garbage collection method that has two phases: the marking phase and the sweeping phase. The marking phase basically is to identify all currently used memory blocks or cells, all currently used cells, because some of them are garbage, they are not currently being used. So go through the whole heap and identify those that are currently being used. Okay, then sweep or reclamation phase. This is the second phase. In this phase, all unmarked cells are returned to the memory pool, so they are swept away and the memory is returned back to the pool. Let's see the two algorithms for the two phases. So the first one that will run is the mark phase, and it's a simple loop. It says for each variable R, mark the object referenced by R as being used. Okay, so all objects that are currently, they have a reference that is referencing them, they will be marked as they are currently being used. So they have a mark. This is being used, this is being used, this is being used, and so on. Now call the sweep. Okay, what will the sweep do? This is the sweep. Say for each object P, so whether the object is being referenced or not, for each object in the pool, in the heap rather, check if the object is marked, then it is being used. So just unmark it. However, if it is not marked, then release it. Okay, so basically it goes through all the content of the heap and release all objects that do not have any marker on them. This is basically what this algorithm will do, the mark and sweep. Okay, so just go through the heap for any variable that is referencing an object, mark that object as being used. Then in the second phase now, check all the objects, all those that do not have any mark, release them. Return the memory back to the pool. This is the idea. Let's look at the other method called the stop and copy. This algorithm collects garbage and also defragments the heap. This is the advantage of this method. In addition to garbage collection, it also actually defragments the heap. How does it work? It divides the heap into two regions, active and inactive. So the heap is divided into two regions, active and inactive. So what will happen is at one particular time, memory will only be allocated in the active part. So any request by a program, the memory manager will will allocate from the active side only. Okay. When the memory in the active region is exhausted, the program is suspended and active objects are copied into the inactive region. But the copying is done contiguously. This is where the defragmentation takes place. So the active part is exhausted. What the memory manager will do is to copy all the blocks that are in the active part, copy them to the inactive part. But the copying is done contiguous, meaning they are put next to each other. And in the active part, one block could be at the top there, another block could be down here. But when copying, they will be put together next to each other. So this is actually what will bring the defragmentation, because instead of having small pieces in different places, now they are together in one block. Okay, so this is the first phase. It will copy all the objects in the active part and put them in the inactive part. And then the active and inactive regions, they will reverse their roles. So now the inactive part becomes the active part. So allocation will continue from that, and the other part that was previously active will now become inactive. So this is how this system works. So when this one also is almost exhausted, it will do the same thing. It will copy all the objects to the inactive and then reverse the role. Okay, so this is the algorithm. Say for each variable R, copy the object referenced by R to inactive, and then swap, after copying all of them, swap the role of inactive and active. So active becomes inactive, inactive becomes active, and allocation continues now from the new active region. This is this stop and copy algorithm or garbage collection method. Final remarks comparing between these two garbage collection methods. So both mark and sweep and stop and copy, they suspend the running of the program while garbage collection is taking place. Okay, this is one of the disadvantages, if you like, of both. Okay, the program has to be suspended while the copying is taking place. Okay, or when the marking is taking place in the case of mark and sweep. Okay, now stop and copy has the advantage that it defragments the heap, whereas mark and sweep does not. Okay, you see, in mark and sweep, the object remained where it was. It was only being marked and then unmarked. It remained where it was. But in the stop and copy, the object is being copied to another location where the objects are going to be next to each other, and therefore the fragmentation will be solved. Okay. Now the other thing is stop and copy. This is another disadvantage. The same thing, you know, in today's world, nothing is free, as I normally say. This has the advantage that it defragments the heap, but it has its own disadvantage. The disadvantage is that it requires twice memory than the mark and sweep. Because remember, the heap is broken into two parts, active and inactive. So at any one time, only half of the memory can be used. The remaining part is being left as inactive. This is the disadvantage of this method. And that brings us to the end of this lecture and the end of our lecture series for this course. Thank you very much. Assalamu alaikum.